Welcome viewers once again to the lecture series on integral equation under the NPTEL courses. In the last lecture we were discussing about the Green's function for linear boundary value problems. Just for a quick recapitulation, you can recall we were dealt with Sturm-Liouville type boundary value problems which are defined by ddx of px dy dx plus qx plus lambda rx yx. This is equal to 0 for homogeneous boundary value problem and this is equal to gx for non-homogeneous boundary value problem, with the separated boundary conditions m1 y a plus m2 y dot a, this is equal to 0, m3 y b plus m4 y dot b, this is equal to 0. This is called the separated boundary condition, where a less than equal to x less than equal to b, p dash x, q x and r x, these are all continuous over the interval a to b, lambda is a parameter. With these assumptions we arrived at the position that solution of this equation can be written as y x, that is equal to minus integral a to b g of x comma s g s ds, where this capital G x comma s is the Green's function, and this particular Green's function we defined as well as derived as this is equal to y 2 s y 1 x divided by alpha for a less than equal to s less than x less than equal to b, and y 1 x y 2 x divided by alpha where a less than equal to x less than s less than equal to b, where this y 1 x and y 2 x, these two functions were the solution of the corresponding homogeneous equation L of y, that is equivalent to, in short if we can write, that is p y dashed whole dashed plus q plus lambda r y, this is equal to 0. This was two linearly independent solution of this equation, and not only they are just linearly independent solution of this equation, there was another restriction based upon which we have constructed the Green's function. Those restrictions was that y 1 satisfies the boundary condition on the right end, that is m3 y 1 b plus y 1 dot b, this is equal to 0, and y 2 x that satisfies the boundary condition on the left, that means m 1 y 2 a plus m 2 y 2 dot a, this is equal to 0. So, based upon this we have constructed our Green's function. Now, in this particular formation, one quantity, that is 1 by alpha, still remains undefined, that we are now going to define along with some discussion on properties of this Green's function. So, now let us look at the properties of Green's function. First of all, you can easily verify that g x comma s is symmetric. is a symmetric function of two variables x and s, that is g x comma s is equal to g s comma x. So, that means interchanging the role of x and s, you can easily verify that this condition is satisfied. Secondly, the important property is that g x comma s, this actually satisfies the boundary conditions. This satisfies the boundary conditions, and of course, you can verify that the g x comma a satisfy this type of m 1 y 2 a plus m 2 y 2 dot a, this is equal to 0. Now, without any loss of generality, if we simply assume the boundary conditions into this particular format, say y a, this is equal to 0 equal to y b, the simplest boundary condition corresponding to m 1 y a plus m 2 y dot a equal to 0 and m 3 y b plus m 4 y dot b equal to 0. So, that means choosing m 2 and m 4 equal to 0, we can arrive at this type of boundary conditions. Now, with this aid, that is y 1 satisfies boundary condition on the right, implies y 1 b, this is equal to 0, and y 2 x satisfies the boundary condition on the left, means y 2 a, this is equal to 0. Now, look at the definition for the Green's function. Green's function is g x comma s, that is equal to here y 2 s y 1 x divided by alpha. This is defined for a less than equal to s less than x less than equal to b, and y 1 s y 2 x divided by alpha, where a less than equal to x less than s less than equal to b. Now, look at this definition. In the first part, x can be equated to b. So, therefore, when you are substituting x equal to b in the Green's function, then g of b comma s, that means we are substituting x equal to b, and from this definition x equal to b is allowed for the when g x comma s is equal to y 2 s y 1 x by alpha. So, this will come out as y 1 b y 2 s divided by alpha, and already we have mentioned that y 1 b equal to 0. So, therefore, this is equal to 0. Similarly, we can easily verify that g a s, that is equal to y 2 a y 1 s divided by alpha, this is equal to 0. So, that means the Green's function satisfies the boundary condition on the left hand point as well as on the right hand point. And similarly, using the property that m 3 y 1 b plus m 4 y 1 dot b, you can verify that they also satisfy the boundary condition when boundary condition given in general format. Thirdly, this g x comma s, this is continuous on this squared domain a comma b cross a comma b, and its partial derivative has a jump discontinuity along the line x equal to s, and this is given by that partial derivative of g x comma s has a jump discontinuity, and which is defined as del x of g x comma s at x equal to s plus. So, that means we have to use the definition x greater than s minus del x of g x comma s at x equal to s minus, that means we have to use x less than s, that is equal to minus 1 by P s. And from here we can easily find out what will be the value of alpha or expression for alpha in terms of s. Now, before proceeding further, I just want to make a remark here that initially we started our discussion on this type of ordinary differential equation subjected to boundary conditions, that is d 2 y dx 2 plus a 1 x dy dx plus a 2 x y equal to capital G x. Purposefully I am writing here capital G x, and with the condition say y a equal to 0 equal to y b. Now, after that we have discussed everything on Sturm-Liouville type boundary value problem. So, the question is, whatever theory that we have discussed on Sturm-Liouville boundary value problem, that can be applied for this type of differential equation or not. So, we can put the question in other way around, that whether this equation can be converted into the Sturm-Liouville boundary value problem format or not, such that the operator will become a self adjoint operator. Answer is yes, this can be done, because that d 2 y dx 2, this equation can be multiplied by the function p x, and which results in p x d 2 y dx 2 plus p x a 1 x dy dx plus p x a 2 x y, that is equal to p x into capital G x, this one. Now, if we define p x, this is equal to e to the power integral a 1 x dx, then we can easily verify that d dx of p x, this is going to be a 1 x e to the power integral a 1 x dx. So, that means actually this is equal to p x times a 1 x. So, if we define p x in this particular way, so the first two term of the last expression, that is p x d 2 y dx 2 plus p x times a 1 x dy dx, these can be combined into to write d dx of p x into dy dx. So, that means this equation becomes d dx of p x dy dx plus q x y, this is equal to g x, where q x is p x times a 2 x and small g x, this is equal to p x times capital G x. And just note that here we have made some rearrangement of the term, or you can say use the transformation p x equal to this one, and in this process we have not disturbed anything on y. So, that means the boundary condition y a equal to 0 equal to y b, that will remains unaltered. So, that means this problem can be written as a Sturm-Liouville boundary value problem. Now, next is that we are going to consider some particular problem, that how this type of boundary value problem can be solved in terms of Green's function. So, first of all we consider this example, that is d 2 y dx 2 minus y, this is equal to f x with the condition y 0 equal to 0 equal to y 1. So, of course, this is a simplified version of the Sturm-Liouville boundary value problem, and at this moment we have no lambda here, p x is 1. So, of course, this is an equation of the form Sturm-Liouville boundary value problem. Now, first of all we have to consider the corresponding homogeneous equation, that is d 2 y dx 2 minus y, this is equal to 0. This is the homogeneous ordinary differential equation associated with the given non-homogeneous problem. Two linearly independent solution of this particular problem are actually cos hyperbolic x and sin hyperbolic x. Now, you can recall, in order to construct the Green's function for this problem, we have to choose y 1 x and y 2 x in such a way that y 1 x will satisfy the boundary condition on the right end and y 2 x will be satisfying the boundary condition on the left end, such that y 1 and y 2, these two functions of x should be linearly independent. Now, clearly for all real values of x, cosine hyperbolic x is always positive. So, that means this cosine hyperbolic x does not vanishes either at x equal to 0 or at x equal to 1, but sin hyperbolic x, this is equal to 0 for x equal to 0. So, that means the sin hyperbolic x, this is a solution of the homogeneous problem and satisfying the boundary condition on the left. So, based upon this fact, we can denote this sin hyperbolic x as y 2 x. Now, we have to find out a linearly independent function which will be satisfying the left end boundary condition. As none of them are satisfying the boundary condition and equation is a linear equation. So, we can try to find out y 1 x into the format that is linear combination of these two functions, that is C 1 cosine hyperbolic x and C 2 sin hyperbolic x, and using the condition that C 1 cosine hyperbolic x plus C 2 sin hyperbolic x will be 0 at x equal to 1, you can find out C 1 C 2 and ultimately we will be having this result, that is y 1 x, this is equal to sin hyperbolic 1 minus x. This can be easily obtained, because if you claim y 1 1 equal to 0, that means y 1 1 equal to 0. So, this implies C 1 cosine hyperbolic 1 plus C 2 sin hyperbolic 1, this is equal to 0, and from here you can find out C 1 by sin hyperbolic 1 equal to C 2 by minus cosine hyperbolic 1, and taking this constant of proportionality equal to 1, you can derive these quantities C 1 and C 2, and after substituting you can find y 1 x equal to sin hyperbolic 1 minus x. And of course, by the method of Wronskian you can verify these two solutions, that is sin hyperbolic x and sin hyperbolic 1 minus x, they are actually two linearly independent solution of the homogeneous equation. So, now with this definition or this particular choice for y 1 x and y 2 x, we can write the Green's function g x comma s, that is equal to 1 by alpha sin hyperbolic 1 minus x times sin hyperbolic s, this is 0 less than equal to s less than x less than equal to 1, and this is equal to 1 by alpha sin hyperbolic x sin hyperbolic 1 minus s with 0 less than equal to x less than s less than equal to 1. So, this is the format. Now, here if we apply the jump discontinuity of the derivative along the line s equal to x, then we can find del x of g x comma s at x equal to s plus minus del x of g x comma s at x equal to s minus, this is equal to minus 1 by 1, because here p x this is equal to 1. So, p s this will be equal to 1. So, this is nothing but minus 1 by 1, and this x equal to s plus. So, that means x greater than s. So, therefore, from this definition of Green's function, we can find this will be actually del x of 1 by alpha sin hyperbolic 1 minus x sin hyperbolic s. Now, we can substitute x equal to s here, because this is actually in order to choose the proper g x comma s, and then minus integral del x of 1 by alpha sin hyperbolic x times sin hyperbolic 1 minus s at x equal to s, this is equal to minus 1, and this gives minus 1 by alpha cos hyperbolic 1 minus s sin hyperbolic s minus 1 by alpha cos hyperbolic s sin hyperbolic 1 minus s, this is equal to minus 1, and this implies sin hyperbolic 1 divided by alpha equal to 1, implying alpha equal to sin hyperbolic 1. So, therefore, finally, for the given problem g x comma s, that is equal to sin hyperbolic 1 minus x sin hyperbolic s divided by sin hyperbolic 1 and sin hyperbolic x sin hyperbolic 1 minus s divided by sin hyperbolic 1. This is for 0 less than equal to s less than x less than equal to 1, and 0 less than equal to x less than s less than equal to 1, and therefore, solution to the given problem y x is equal to minus integral 0 to 1 g x comma s, then f s ds, and that is equal to, you can find that minus integral 0 to x sin hyperbolic 1 minus x sin hyperbolic s divided by sin hyperbolic 1 f s ds minus integral x to 1 sin hyperbolic x sin hyperbolic 1 minus s divided by sin hyperbolic 1 f s ds. So, this is the solution to the given problem in terms of Green's function, and if we know the particular form of f s, then we can find out the complete solution of the given problem. And at this moment it comes to your mind that this course is on integral equation, but I am here discussing a solution of the Sturm-Liouville boundary value problem, which is a differential equation. But the point I like to make it clear here, that if we convert the given differential equation into the associated Fredholm integral equation of first or second kind, that will come out after the derivation, and actually f x is non-zero. So, it will be non-homogeneous Fredholm integral equation of the second kind, then you can verify for that problem this is going to be the solution of the integral equation. Now, we consider one more example where f x is given such that you can verify the solution obtained by this method is actually satisfying the given equation. Here we consider the problem, that is d 2 y dx 2 plus y, this is equal to 1 plus x with the condition y 0 equal to 0 equal to y pi by 2. So, now this corresponding homogeneous equation d 2 y dx 2 plus y equal to 0, it has two linearly independent solution, one is sin x, other is cos x, and clearly this cos x satisfies the boundary condition at x equal to pi by 2, sin x satisfies the boundary condition at x equal to 0. So, that means sin x satisfying the boundary condition on the left end, cos x satisfying the boundary condition on the right end. So, therefore, we can denote them as cos x as y 1 x and sin x as y 2 x, and therefore, this Green's function g x comma x, this will be sin s cosine x divided by alpha, this is for s less than x, and cosine s sin x divided by alpha, this is for x less than s. And again using the jump discontinuity of the Green's function, that is the derivative of the Green's function, we can find del x of g x comma s for x greater than s. So, that means here we have to apply on sin s cosine x, then substituting x equal to s, minus del x of cosine s sin x divided by alpha with x equal to s, that is equal to minus 1, because p is equal to 1 here. So, this gives minus sin square s divided by alpha minus cosine square s divided by alpha, this is equal to minus 1, implying alpha equal to 1, and therefore, this Green's function g x comma s, this is equal to simply sin s cosine x and cosine s sin x, this is valid for 0 less than equal to s less than x less than equal to 1, and this is 0 less than equal to x less than s less than equal to 1. So, these are the definitions, and therefore, the solution to the given problem, that is y x is equal to minus integral 0 to pi by 2 g x comma s, this will be 1 plus s ds. So, first of all we have to divide into two intervals, that is 0 to x g x comma s 1 plus s ds minus x to pi by 2 g of x comma s times 1 plus s ds, and here this will be minus integral 0 to x, first integral s is less than x. So, whenever s is less than x, so this is sin s cosine x. So, therefore, this will be sin s cosine x 1 plus s ds minus integral x to pi by 2 cosine s sin x 1 plus s ds, and using the formula for integration by parts, cosine x can be taken out of the integral, and then we have to use the by parts formula, considering 1 plus s as the first function u and sin s as the second function v. So, we will be having this minus 1 plus s cosine s, because integral of sin s is minus cosine s, then by parts will involve one minus sign combined with this one plus 1, derivative of 1 plus s is 1. So, plus cosine s, and after integration this will be plus sin s limit 0 to x, and for the second integral minus sin x can be taken out of the integral sign, then it will be 1 plus s sin s plus cosine s limit x to pi by 2, and this is equal to minus cosine x at the upper limit minus 1 plus x cosine x plus sin x at the lower limit. Cosine 0 is 0. So, this will be plus 1 and no contribution from the sin s term, then minus sin x, this will be 1 plus pi by 2 into 1, sin s is 1, there is no contribution from cosine, at pi by 2 it is 0, and then minus 1 plus x sin x minus cosine x. Now, you just check that these two terms can be combined together, this one and this one, they actually produce the term 1 plus x, and then these two terms cancels with each other, that is this one and this one. So, then we are left with minus sin x minus cosine x and minus pi by 2 sin x. So, this is actually solution of the non-homogeneous boundary value problem, that is d 2 y dx 2 plus y equal to 1 plus x subjected to the boundary condition, that is y 0 equal to 0 as well as y pi by 2 that is also equal to 0. Next, we are going to consider some properties of eigenvalues and eigenfunctions associated with the Sturm-Liouville boundary value problem, from where we can define that set of orthogonal functions, and the infinite collection of set of orthogonal functions will give us opportunity to expand any given function, which of course satisfies certain differentiability and continuity condition, such that the infinite series will converges uniformly. Then those functions can be expressed as an infinite series of these orthogonal functions, that means those functions can be generated with the help of the collection of family of orthogonal functions. Now, first of all we consider some particular properties of this problem. So, throughout this rest of the part of the discussion, we will be considering this equation, that is d dx of p x dy dx plus q x plus lambda r x, this y equal to 0 with the boundary conditions, that is separated boundary conditions m 1 y a plus m 2 y dot a, this is equal to 0, and m 3 y b plus m 4 y dot b, this is equal to 0, where this p dot x, q x and r x, they are continuous, and we are assuming that p x is non-zero for all values of x within the range, that is x belongs to this closed interval a comma b. Now, first of all we are going to prove a result, that let y x and z x are solutions of the Sturm-Liouville boundary value problem corresponding to lambda and mu respectively with lambda not equal to mu. Further, this condition, that is P x and Wronskian of y x z x, this is from a to b is equal to 0, then integral a to b r x y x z x dx, this is equal to 0. And here, just for your quick reference, Wronskian of y x and z x is nothing but the determinant y x z x y dash x z dash x. So, that means for lambda y is the solution, for mu z x is the solution. If this condition, that is P x multiplied by Wronskian of y z from a to b, this is equal to 0, then this condition is satisfied, a to b r x times y x z x dx equal to 0. And whenever this condition is satisfied, that means integral a to b r x into y x into z x equal to 0, then we say that y and z, they are orthogonal functions to each other with respect to the weight function r x. Depending upon the associated Sturm-Liouville boundary value problem, if r x equal to 1, then condition for orthogonality will comes down to simply integral a to b y x z x dx, this is equal to 0. So, first of all we prove this result. Y x is the solution of the Sturm-Liouville problem for lambda. So, that means d d x of p x dy dx plus q x plus lambda r x, this times y x, this is equal to 0, call it 1, and d d x of p x dz dx plus q x plus mu r x multiplied by y x, this is equal to 0, call it 2. Now, if we multiply second equation by z x and first by y x and then subtract, this implies we will be having that, multiplying 2 by y x and 1 by z x. Then we can find that y x multiplied with d d x of p x dz dx plus q x plus mu r x, this into y x z x minus z x multiplied with d d x of p x dy dx minus q x plus lambda r x times y x z x, this will be equal to 0. Here in equation 2, this will be actually z x. Now, you can see that q x y x z x and q x y x z x cancels with each other. So, then rest of the expression we can combine as y x with d d x of p x dz dx then minus z x times d dx of p x dy dx, this expression plus mu minus lambda r x y x z x. And now you can recall from the previous discussion that this part, that is y x d dx of p x dz dx minus z x d dx of p x dy dx, this is nothing but the derivative of p x multiplied with y x z dash x minus z x y dash x, this equal to lambda minus mu r x y x z x, and this expression y z dot minus z y dot is nothing but the Wronskian of y and z, and therefore, we can write that d of p x w y x z x, this is equal to lambda minus mu r x y x z x dx, and then integrating from a to b, we can find p x w y x z x, this limit a to b, that is equal to lambda minus mu integral a to b r x y x z x dx, and since this is given to be 0 and with the condition lambda not equal to mu, this implies that integral a to b r x y x z x dx, this is actually equal to 0. So, that means for two Sturm-Liouville boundary value problem, one with parameter lambda and other with parameter mu, with same p q r, if we are able to find out two corresponding solution of the equations which are denoted by y x and z x, such that p x Wronskian of y x z x evaluated at b minus the same expression evaluated at a is equal to 0, then these two functions y and z are orthogonal to each other with respect to the weight function r. Next, we are going to prove that for a particular Sturm-Liouville boundary value problem, we are able to find out two non-trivial solutions, that means eigenvalues and eigenfunctions, and if two eigenfunctions are corresponding to two distinct eigenvalues, then those eigenfunctions are actually orthogonal functions. So, in order to prove this, first of all we are going to prove this result, that let y m x and y n x be two eigenfunctions of the Sturm-Liouville boundary value problem. In short, we can write p y dot whole dot plus q plus lambda r y equal to 0, where x belongs to a comma b, with the boundary conditions m 1 y a plus m 2 y dot a equal to 0 equal to m 3 y b plus m 4 y dot b, corresponding to two distinct eigenvalues lambda m and lambda n respectively, then P x Wronskian of y m x y n x a to b, this is equal to 0. This is one of the important result that we can prove. So, if we look at this expression, that is P x Wronskian y m x y n x a to b, this is equal to P of b y m b y n dot b minus y n b y m dot b minus P a multiplied with y m a y n dot a minus y n a y m dot a, this is equal to 0. We have to prove this. Now, recall that whenever we have mentioned that the boundary condition, then we have mentioned m 1 and m 2 are not simultaneously equal to 0. Now, y m and y n, they are solutions of the Sturm Liouville boundary value problems, because they are the eigen functions. So, that means y m satisfies the left hand boundary condition, that is m 1 y m a plus m 2 y m dashed a, this is equal to 0, and m 1 y n a plus m 2 y n dot a, this is equal to 0. Now, without any loss of generality, we can assume that m 1 this is not equal to 0, because initially we have mentioned that m 1 and m 2 are not simultaneously equal to 0. So, therefore, we are assuming m 1 not equal to 0. If m 1 not equal to 0, then from the first relation we can write m 2, this is equal to minus m 1 y m a divided by y m dash a. So, that means then we can substitute this m 2 in this expression. So, that means eliminating m 2 between these two relations, we can find m 1 times y m a y n dot a minus y n a y m dot a, this is equal to 0. Now, already we have assumed m 1 not equal to 0. So, therefore, we must have y m a y n dot a minus y n a y m dot a, this is equal to 0. Now, of course, with the assumption m 2 not equal to 0, you can arrive at the same result, as well as if m 1 and m 2 both of them are not equal to 0, then in that case also you can arrive at the same result. Here for simplicity, I have proceeded with this assumption, that is m 1 not equal to 0. So, this is equal to 0. Similarly, from the second condition, now you can easily guess that from the second condition we will be able to derive that y m b times y n dot b minus y n b times y m dot b, this is equal to 0. So, combining these two results, that is y m y n dot a minus y n a y m dot a equal to 0, and then y m b y n dot b minus y n b y m dot b, this is equal to 0, you can derive that P x Wronskian of y m x y n x from A to B, this is equal to 0. So, that means from this result we can conclude that for a Sturm-Liouville boundary value problem, if y m x and y n x are two eigen functions corresponding to two distinct eigenvalues lambda m and lambda n, then they are orthogonal to each other, because in the last result we have established if y z are two solutions such that p x w of y x comma z x from A to B, this is equal to 0, then integral A to B r x into y x into z x, that is equal to 0. So, combining these two results, we can say that lambda m comma y m x is an eigenpair, lambda n y n x, this is another eigenpair associated with the homogeneous Sturm-Liouville boundary value problem L y equal to 0 with the separated boundary conditions, and lambda m not equal to lambda n, then integral A to B r x y m x y n x dx, this is equal to 0. So, this is the result. So, that means two distinct eigen functions corresponding to different eigenvalues lambda m and lambda n, they are orthogonal to each other. So, that means today we have established this result. In the next lecture, we will be proving that under certain conditions satisfied by R x, that means if R x maintains the same sign throughout the interval A to B, then all the eigenvalues are real, and then we will define the important class of functions associated with the orthogonal functions, that is family of orthonormal functions, and from there we can find either the Fourier series expansion when the function, these orthogonal functions are trigonometric functions, or in general expansion of a function in terms of infinite dimensional orthonormal functions, such that every function can be expressed as a linear combination of those functions, and we will be discussing how the coefficients of those series in terms of the orthonormal functions can be derived using all these properties of the eigen functions associated with a Sturm-Liouville boundary value problem. Thank you for your attention.